so we will start this module with the equation number 4 of the R equation. I said in the previous module, but before I go for the equation number 4, from the equation number 4, I would like to go back to the previous slides, because there was some confusion. If you should not have this confusion there, where it was at this point. Okay, so initially in the previous module I said this f rho divided by 4 and this f rho divided by rho I cut. So this is not, this remains as such. Then only you have 1 over rho here. Okay, this plus f rho divided by 4 and this minus f rho divided by 4 will go, and you will have 1 by rho here instead of 1 by 4. Okay, so this you just correct in the previous module, and then again from equation number 4 we will start. This equation number 4 we got, and from there I say that this equation is an identity in rho, and so therefore the coefficients of individual power of rho gets vanished. Taking coefficients of rho raised to the power s. Look at the rho raised to the power s. This is here you have rho raised to the power s. Here you have, so L into L plus 1 is one coefficient. Then where else you have rho raised to the power s? You have rho raised to the power s here also. Okay, rho raised to the power s. Then you have rho raised to the power s. So this and this we can take, and so you have coefficient s into s minus 1 plus 2s minus L into L plus 1 is equal to 0. Okay, we can write. So for rho raised to the power s, the coefficient is this one. Since the equation is in terms of identity of rho, so all coefficients of individual power of rho must vanish, so that the equation becomes equal to 0. So you have, for only one example, rho raised to the power s I have taken. So we can write s into s minus 1 plus 2s minus L into L plus 1. You rearrange this one, s square minus s plus 2s is equal to L into L plus 1. Also s square minus s and plus 2s, so plus s is equal to L into L plus 1. So s into s plus 1 we can write s square plus s. So s into s plus 1 is equal to L into L plus 1. Okay, and what does it tells you? Therefore, either s is equal to L or s is equal to minus L plus 1. You see, L is already known to you. L is what? Azimuthal quantum number, which you got in theta equation. So now here we are getting s, and I have written s is equal to s multiplied by s plus 1 is equal to L into L plus 1. What does it means? It means s is equal to L. Then only you can write it like this one, or you can write this also if s is equal to minus L plus 1, that you can check. If you write s is equal to minus L plus 1, then also you can write the previous equation, that s into s plus 1 is equal to L into L plus 1. Okay, in both the condition this equation is to be followed, either s is equal to L or s is equal to minus L plus 1. But the second value does not lead to an acceptable wave function. So what you say, s is equal to L. Now your s is L means s is actually azimuthal quantum number values, remember this one. And if that is so, then f is equal to rho raised to the power L, a small l into multiplied by L, because initially your this f came and from this point f was this one, rho raised to the power s into capital L. So now since s is equal to a small l, so you can write f is equal to rho raised to the power small l into L. Okay, and if you substitute this all L values, a small l for the s, then your equation number 4 will be what? Rho s plus 2 it was there, now L plus 2, d square L divided by d rho square. Rho again s plus 1 was there, so L plus 1. Okay, then again 2L dl divided by d rho. Okay, you just compare with the previous equation number 4. Equation number 4 you have 2s rho s minus 1. So this s again is L, 2L rho s L minus 1. So it's just replacing this equation will give you all s is replaced by a small l in this equation of equation number 4. Okay, and you get this one. Now for this equation, rho L plus 2 d square L by d rho square, rho L plus 1 2L dl divided by d rho same, plus L into L minus 1 plus 2L minus L into L plus 1 rho raised to the power L into L. So, rho raised to the power L into L is this one, rho raised to the power L into L is this one, and rho raised to the power L into L is this one. So, combine these three, 1, 2 and 3 and you get this equation. Okay. You can see L into L minus 1, then 2L and then minus L into L plus 1. Okay. And this is the rho raised to the power small l multiplied by capital L. Then you have this equation 2 rho L plus 1 dl by d rho minus rho L plus 2 dl by d rho minus L rho L plus 1 into L, then plus lambda minus 1 rho L plus 1 into L. Okay. A little more rearrangement, and then what do you get? If you open it up, what do you get? L square minus L plus 2L minus L square minus L. Okay. And then rest of the thing is same, I think, and then you have this equation rho L plus 2 d square L by d rho square 2L rho L plus 1 plus 2 rho L plus 1 minus 2 minus rho L plus 2 plus lambda minus 1 rho L plus 1 minus L rho L plus 1 into capital L. So, you look at this one, this will remain same, this we have this minus L 2L, so this will go, okay, 2L and 2L will go, you have L square minus L square, so this will also go, and you have 2 rho L plus 1 dl divided by d rho, rho L plus 2 dl divided by d rho, okay. So, this will be what? Rho L plus 1, rho L plus 2, and this is rho L plus 1 into L, rho L plus 1 into L. So, you can combine these. Okay. So, this combination will ultimately result into, you can see, ultimately result into this equation, rho L plus 2 d square L by d rho square, dl by divided by d rho terms we at one place and L terms on. What you have to do is your motto should be that double differential equation should be on one side, double differential of L should be on one side, then single differential and then L value. So, d square L by d rho should be first term, then d by d rho of L should be on in the middle, and then L should be on the right hand side of the equation. So, you combine all these terms and you get this value. And if you divide it by rho L plus 1, you get simpler equation, rho d square L by d rho square, dl divided by d rho becomes equal to this one and then this one. So, you get equation number 5. This equation is called Laguerre, is similar to Laguerre differential equation. You remember this term? In case of harmonic oscillator, I said you Hermite differential equation. In case of theta equation, I said you Legendre differential equation. In case of R equation, I am saying Laguerre differential equation. And so that the value of L can be expressed in power series of rho. Okay. So, the value of L can be expressed in power series of rho, and we can write A naught, A1 rho, A2 rho square, A3 rho cube, A4 rho 5 and so on. And if it is so, then we can take the differential. We are repeating same thing time and again, you remember, you should not get confused. You started with R, then went for S, then went for F, then went for L. Okay. So, these are the terms which you are doing time and again, okay, in the series. So, now we are at the stage of L. So, dl divided by d rho is A1, 2 A2 rho, 3 A3 rho square, 4 A4 rho cube and so on for nth term. So, d square L by d rho square you can write for nth term, okay, and for 2 A2, 6 A3 and so on. This you have already done. If you put these values in equation number 5 for L, for dl by rho and d square L by d rho, again you get a big equation which just looks big, but it is very simple, concept is simple. So, it is d square L by d rho square, first differential, then you see L is here, L was the first equation, A naught, A1 rho, A2 rho, A3 rho 3, A4 rho 4, A5 rho 5 and to this one. Then the second differential of this equation was this one, this is your L, this whole is your L. Then this is the first differential. This part is first differential, dl by d rho, and you can look at here itself. If you differentiate, a naught will go because a naught is a constant, no rho you have, but you will have a1 for the first differential, a2 into 2 rho. So 2a2 rho will be the differential of this one. 3 rho square a3. So 3a3 rho square is the differential of this one. Same way 4a4 rho cube is the differential of this one. So this is the first differential term. Now differentiate this one and you get this term. This whole term is the second differential, d square L divided by d rho square. So differentiate this one, a1 term will go, but 2a2 will be the first term. Okay. Then 3a3 will be the first term. Okay. 3a3 means multiplied by 6, so 6a3 rho square will be the term. Then 4 multiplied by 3 will be 12, 12a4 rho cube will be the first term. Okay. 2a2 rho should not be here, I think. Okay. So these are the terms. Now it is equation number 5 with L value written in power series. And now what you do, you again, for this to be valid, what you need? You need to separate the coefficients of each power of rho and equate it to 0, which we have done earlier also. So look for the terms where rho is equal to 0. So terms where rho is equal to 0 is the first term is which one? Which one is the first term? This one is the first term, a1. Here you do not have a rho, so the coefficients is 2 into L plus 1 into a1. 2L plus 1 into a1 is the first term. Then another term where rho is not present is this term a naught in the L value, a naught in the L value. So what is the coefficients? Lambda minus 1 minus L into a naught, lambda minus 1 minus L into a naught. So for rho raised to the power 0, the coefficients is 2L plus 1, 2 within bracket L plus 1 a1 plus lambda minus 1 minus L a naught is equal to 0. What about coefficients number? Second coefficients of rho raised to the power 1. So coefficients raised to the power 1 is, I think this is there somewhere if I go back, equation number 5. So rho is already there here, rho is there, so it should be there. Okay. So it is there, it will not go. Okay. So coefficients of rho raised to the power 1 will be 2a2, then second term will be 2a2 L into 2a2 2L plus 1, 2L plus 1. Then the third will be this one, a1, and then this a1. So you have minus a1 plus a1 multiplied by lambda minus 1 minus L. So you rearrange this one, you get this one. Same way, rho raised to the power 3, rho raised to the power 4 you can separate, and finally you can separate it. Rho raised to the power 2 also is separated, 3 also is separated, and rho raised to the power n we can separate. And if you separate rho raised to the power n, and here only thing is n is equal to v, if I write, then you can write it like this one. Okay. Lambda minus L minus 1 minus lambda minus L minus 1 minus n, an 2 into n plus 1 into L plus 1, then n into n plus 1, an plus 1 was the equation. So I have replaced this n with v, and now I am writing lambda minus L minus 1 minus v is equal to av, then 2 into v plus 1, L plus 1, v into v plus 1, a v plus 1. So if you rearrange this one, this equation is equal to 0, where v is 0 or integer. So if you rearrange this one, you can write it this one, a v plus 1 divided by a v is equal to minus lambda minus L minus 1 minus v, divided by 2 V plus 1 L plus 1 V into V plus 1. Okay. So, this either this N or V is what? This N or V is power to the rho raised to the power 0, rho raised to the power 1, rho raised to the power 2. So, this N or V could be either 0, 1, 2, 3. V could be either 0, 1, 2, 3, 0 or any integer. Okay. So, we got this equation, and a similar equation we got in two different derivations earlier also, in simple harmonic oscillator and in rigid rotor, where theta equation we did. So, at two different places we have got this equation. This is called recursion formula. This is called recursion formula for equation number 5. Okay. And now, if the solution of the main equation is acceptable as a wave function, the series should break after a finite number of terms, because the series has to break, because finite number of terms you want to be an acceptable solution. And if it has to break, what we did earlier, that the numerator of the recursion formula should be equal to 0. This we have done earlier also. So, numerator is lambda minus L minus 1 minus V, lambda minus L minus 1 minus V, or I have written NR, no issue, N, V, NR all are same. Okay. So, NR is equal to 0. This NR has an integral value 0, 1, 2, 3, because so obviously this N was rho raised to the power 0, rho raised to the power 1, rho raised to the power 2. So, NR can have any value from 0 to 0, 1, 2, 3, 4 up to N. And if you rearrange this equation, what do you get? Lambda is equal to L plus 1 plus NR. This you can write, L plus 1 plus NR. Then N is equal to L plus 1 plus NR. And therefore, this N, which is lambda is equal to N, is always greater than L plus 1 or equal to L plus 1. When azimuthal quantum number L is equal to 0, okay, then N will be equal to, L is equal to 0 means N is equal to 1. This NR, the name NR is given to radial quantum number. This can have any value 0, 1, 2, 3, 4. Okay. And this N, which is lambda is equal to N, is called principal quantum number. So, you got principal quantum number value in the solution of radial equation, radial part of the hydrogen atom solution. Okay. This NR can have any value 0, 1, 2, 3, but N will not have 0 value, N will have 1, 2, 3, 4 values, okay, because N is L plus 1 plus NR. Okay. So, NR can have, if NR is 0, then also you have L plus 1 values, and L is 0, if NR is 0 and L is 0, then also N is equal to 1. Okay. So, N can have minimum value 1, but NR can have 0, 1, 2, 3, 4 values. This NR is simply the coefficients, simply the power with which the rho term is raised. Okay. So, this NR, V, first N, all was the same thing. Okay. But this N, which is principal quantum number, is actually lambda, and this lambda we say that N is always greater than L plus 1, L plus 1 plus NR. Okay, will give you this one. Okay. Well, the minimum value of N, that is principal quantum number, is unity. So, principal quantum number you got from the solution of radial wave functions. Now, further equation 5 may be written as rho is equal to d square L by d rho square, dl by dy 2 into L plus 1 minus rho, lambda minus 1 minus L into capital L. Now, I have just simply replaced, this was the equation number 5 earlier. Now, replace this with the principal quantum number N. That is all. Okay. And I have written this as a double prime for the double differential equation, single prime for the first differential dl divided by d rho. So, this equation number 5 is very similar to the associated Laguerre equation. This is your associated Laguerre equation, and this is your equation number 5. So, compare this and then you can say that you can get a solution of equation number 5 in terms of associated Laguerre polynomial. So, the radial wave functions, substituting lambda is equal to n equation number 5 gives you this one, n minus 1. This was lambda earlier, now it is n minus 1, which is principal quantum number. Now, substitute 2l plus 1 is equal to p, 2l plus 1 is equal to p, and you get this equation. This equation is known as associated Laguerre equation, and the solution of this equation will be associated Laguerre polynomial, or more correctly the associated Laguerre polynomial multiplied by a constant factor. Okay. This associated Laguerre polynomial we write as this one, multiplied by a constant factor, and in fact this p and n prime is actually L 2l plus 1 divided by n plus 1 multiplied by, where c is a constant and may be made equal to normalization factor. So, this c is the normalization factor, and the solution of equation number 5 is this one, L Laguerre polynomial, associated Laguerre polynomial is 2l plus 1 n plus L into rho multiplied by normalization constant. This is the solution of equation number 5. Okay. So, what is the normalization factor again? The question is, so if you have got the solution, radial wave function solution in terms of associated Laguerre equation, associated Laguerre polynomial, then the task is to get the normalization factor, and if you normalize that factor, it is again the same in the different form I have written, rho L R S double is the double prime second differential equation, then S plus 1 minus rho. This is a standard form of associated Laguerre differential equation. So, a standard form of associated Laguerre equation, if I write S plus 1 minus rho is equal to this one and then R minus, then we say that the differential equation is satisfied by L R S rho, which we say the sth derivatives of the rth Laguerre polynomial, the sth derivatives of the rth Laguerre polynomial is called the associated Laguerre polynomial of degree R S and degree R and order S, degree R and order S. Okay. And this degree R and S, associated Laguerre polynomial of degree R and S is given as ds divided by d rho S into LR rho, and again LR rho is Laguerre polynomial. This is associated Laguerre polynomial. So, the same situation arises which we came across in theta equations, that we got Legendre polynomial and associated Legendre polynomial. Here we are getting Laguerre polynomial and associated Laguerre polynomial. Okay. If we now replace R by n plus L and S by 2l plus 1 in the above equation, we obtain rho L, and if you replace this one, you get this equation, and for that the solution is this one. On comparing this with equation number 5, we obtain that the treatment of R equation of the hydrogen atom by the polynomial method, we see that the two equations have the same identity, and then you can write the solution RR in terms of associated Laguerre polynomial like this one. Exponential minus rho divided by 2 was the first term which you got while getting an asymptotic solution. So, I said any solution of the radial wave function will have this term. So, you do have this term. In addition to this, you have L into associated Laguerre polynomial multiplied by a constant term, rho raised to the power L. So, these functions are called associated Laguerre functions. Now, once you have this function, then we can go ahead and we can calculate different associated Laguerre polynomials, and we can calculate different associated Laguerre polynomial also. Okay. So, if I express this explicitly, this polynomial could be expressed like this one, it is not of much use. But if you normalize this wave functions, normalization of the radial wave functions, then what you can do? This was your radial wave function. So, now this is the normalization condition, RR into RR star is equal to R square, dr is equal to 1. And if you try to normalize this, then for normalization what you say, here the factor R square is necessary to convert the length dr in element of volume. So, we write, now you go back to the same equation which I have written when we were doing the changing of variables. So, rho is equal to 2 alpha r, alpha square was this one and this you know. So, lambda was this one and this lambda became equal to n. So, alpha becomes equal to mu z E square divided by h cross square n. Alpha becomes equal to this alpha becomes equal to mu z E square divided by h cross square into n. And so, rho becomes equal to 2 alpha r, and alpha you know 2 mu z E square divided by h cross square n into r. Then again you can write 2r divided by n and 2r divided by n, then mu z E square divided by h cross square. So, you can write 2 zr divided by n 4 pi square mu E square divided by h square. So, h square I have converted into h square divided by 4 pi square. So, you can write it like this one. Z is always 1 because we are talking about hydrogen atom, that is 1. Okay. So, we can write 2 zr by n, and this equation 4 pi square mu E square by h square is the equation for, do you remember what is this equation? This is 1 by a naught, that is Bohr's radius, that is Bohr's radius. So, we have got a relation between rho and Bohr's radius. Okay. So, if you write this A0 is Bohr's radius. So, what you write? Rho becomes equal to 2 zr divided by Na0. So, this is important now. This your rho variable is actually 2 zr divided by Na0, and Z will become equal to 1 for hydrogen atom. Okay. And so, if rho can be written in terms of A naught, then R also can be written in terms of A naught, because rho was 2 alpha r. So, if you write R in terms of A naught, then you can write Na naught divided by 2Z into rho, and then dr will be equal to Na naught divided by 2Z into rho. So, if you have these in terms of A naught, then you can find the normalization constant. So, the normalization constant is, this is your function, then exponential minus rho divided by 2, and rho divided by 2 will be minus rho, and then rho divided by 2L, because 2 functions you have. So, 2L. So, this is also 2 functions, this is also 2 functions, we have summed up, and then you have L into 2L plus 1 n plus 1 n plus L into rho. Then for RS Na naught divided by 2Z rho square, what was this? Na naught divided by 2Z rho, R square was there. So, Na naught 2Z into rho is the square of this function, and then you have dr, which is equal to this one. So, if you differentiate this one, what you get is actually this one. The normalization constant is now 2n into n plus L factorial whole cube, the n minus L minus 1 factorial. So, this is your normalization constant n for the wave function. So, the total normalized wave functions you can write is n is equal to root under 2z divided by n naught whole cube, n minus L minus 1 factorial, 2n n plus L factorial. Okay. So, this was your integral, and now it is n square multiplied by this one. So, if you write n square multiplied by this one, you get, this is your normalization constant. And in terms of this normalization constant, your radial wave functions are, now we have two different quantum numbers which is important, n and L. You see L is also here, m does not appear here, but R depends on n principal quantum number and L azimuthal quantum number. So, R n L R is actually 2z divided by n naught whole cube, n minus L minus 1 factorial, then 2n n plus 1 factorial whole cube, exponential minus rho it was there. So, 2 zr divided by Na0, zr divided by Na0, 2 zr divided by Na0 raised to the power L. Then you have, you see, it was rho divided by 2. This was exponential minus rho divided by 2. So, exponential minus 2 zr divided by Na naught and divided by 2. So, 2 is gone, minus zr divided by Na naught, because this is rho raised to the power L. So, it is 2 zr divided by Na naught raised to the power L, and then 2L plus 1 n plus 1 2 zr divided by N, this was rho. Okay. So, this is your final solution of Schrodinger wave equation for radial part of the wave function for hydrogen atom. Now, in order to get the actual value of these functions for different cases of n and L, you will have to find out associated Laguerre polynomial, and this associated Laguerre polynomial is related to Laguerre polynomial. Okay. So, this is again the same thing in terms of rho and in terms of L, in terms of rho and 2 zeta divided by n naught factor. So, this is the radial part of the wave function. So, in order to find out the first few energy levels, the radial parts of the wave functions, we will try to find out different values of Laguerre polynomial, associated Laguerre polynomial and Laguerre polynomial. Once you have these values of Laguerre polynomial and associated Laguerre polynomial, then you can calculate for individual values of n and L, and you can find out the radial part of the wave function. So, this will be the part of next module. We will try to calculate the radial part of the wave functions for first few energy levels of the solution of hydrogen atom, radial part of the hydrogen atom. And then we will try to interpret the angular part and the radial part of the wave functions separately, so that you can have an idea about how the electron probability will vary in case of hydrogen. And whatever information you already have, we will try to see whether we get the same information from these quantum mechanical calculation or not. Okay. So, all this will be the part of the next modules. Okay. Thank you.